This tutorial covers the basics of the trigonometry used in the Physics 103, 104 courses, particularly in lecture. Now in lab, you're likely to go beyond what's shown here, but at least this will be a foundation to work from. Now, even though we live in a three-dimensional environment, we are going to stick to strictly two-dimensional trigonometry. And the reason for that is 3D trig is extremely complex, and we dare not go there. The two dimensions can be represented graphically by a pair of axes. One is often called the x-axis, and it's usually the horizontal axis. And another is called the y-axis normally, and it's the vertical axis. Straight down, we usually say that's the negative y direction, and to the left, we usually say that's the negative x direction. Where the axes cross, that's a 0, 0 coordinate, also known as the origin. In physics, we often deal with vectors, and in two dimensions these are represented as arrows, and one is shown here in purple, and I'm going to call this vector r because it's kind of like a radius of a circle. The notation that is usually used goes like this. R by itself represents, or is equivalent to, the magnitude of the r vector. So it's the length of the vector. And that's not the same as the full r vector. When we talk about a full vector, all the properties of the vector, we have to provide the length and the direction, or we can provide, in two dimensions, we can provide the x and the y components. The red arrow, which itself is actually a vector, represents how much in the x dimension the r vector is, and I'm going to write it as r subscript x. The blue arrow, which is also a vector, represents how much the r vector in purple is going in the y dimension. So I'm going to label it r sub y. The direction of the r vector shown in purple can be defined either by its angle relative to the x-axis, shown here by theta x, or by its angle relative to the y-axis, shown here as theta y. The relationship between theta x and theta y should be quite obvious because together they have to add up to 90 degrees. So we can write that theta x plus theta y equals 90 degrees. And so that means that theta y must be 90 degrees minus theta x. The components of r vector, which are rx and ry, are themselves vectors, and in terms of vector addition, rx vector plus ry vector in fact equals r vector. However, in terms of magnitudes, which are the lengths of these arrows represented on the diagram, the length of Rx vector plus the length of Ry vector does not equal the length of R vector. To determine the lengths of Rx and Ry, we have to do some trigonometry. Now in here, for the case of Rx, you can see I've got a right triangle in there. And that means that the length of Rx because it's connected to theta x is going to be the length of vector r times the cosine of theta x. So if a side is connected to an angle, it's the cosine. Now the vector Ry has the same length as this side of the orange triangle. So that means that the length of the Ry vector will be the length of the R vector times the sine of theta x, because sine means separate and cosine means connected. Rx and Ry can also be calculated using theta y, because here we have another right triangle, and Rx is the length of this side of the green triangle, which is separate from theta y. So we can also write that Rx equals the length of R, separate is sine theta y. It's separate from the theta y angle. And similarly, you can see that the vector Ry in the green triangle is connected to theta y. So Ry equals the length of vector R cosine theta y. So what do we do if we know the lengths of the Rx and the Ry vectors, but we don't know the length of the R vector? Well, we apply the Pythagorean theorem to either the orange triangle or the green triangle, because the purple R vector, the length of it is the hypotenuse of either of those triangles, and the square of the hypotenuse is the sum of the squares of the two sides. So we can write that R squared equals Rx squared plus Ry squared. So this means that R, which represents the length of the R vector in purple, equals the square root of Rx squared plus Ry squared. If we want to calculate what theta x and theta y are, we can note that the tan of theta x, and looking at that orange triangle, must be Ry over Rx. And this is the TOA in SOCAR TOA. Tan is opposite over adjacent. The Ry is opposite the theta x angle, and the Rx is adjacent to the theta x angle. So it follows that theta x is the inverse tan of ry over rx. Now this analysis that I have done is being purely in the first quadrant where everything is positive. In the second quadrant over here you can do a similar analysis, but note that Rx, the length of the Rx vector, will be considered negative, Ry is still positive. In the third quadrant, Rx and Ry, their lengths are considered both negative. And in the fourth quadrant, Rx is positive but Ry is negative.